SwayamPrabha. Digital India. Educated India.
Welcome to this lecture number 19 on control systems. That is, last class we talked about the position regulator. So this class what we'll be talking about is control of nonlinear systems. Okay, so we had discussed that a robot manipulator is essentially a nonlinear system, and we'll see how to deal with nonlinear systems. Then we'll talk about stability, a little bit on stability, and then talk of robot specifications, that is accuracy, resolution, and repeatability. So I'll just minimize the screen and put off the video. It's not required. So let's start off today with nonlinear control of manipulators. Now, in the last class, what we looked at is design of proportional controllers, then proportional plus derivative controllers, and then proportional integral and derivative controllers. Now, what we were talking about are essentially what we call position regulators. That means we are required to keep the link or the mass, in the case of a spring mass damper, in a particular position, and there are some disturbances which are acting on the mass, and the controller has to basically keep the position, keep the block in a particular position. Okay. Now today we'll talk about trajectory tracking controllers. So today let's start on trajectory tracking. So trajectory tracking. Now, what we mean by trajectory tracking. So we know that a robot link like this has to go from some position to some other position in some time t. Okay, so it has to go from here to maybe the next position in some time from here to here. Okay. Now, how the trajectory tracking controller works is that instead of operating in the x domain or the position domain, it basically generates an error and then starts operating in the error domain. Okay, so what it basically does, it defines a servo error. So we define a servo error called E, which is given by theta d, that is the desired position minus the present position. Okay, and then we try and make this error go towards 0. Now, how do we generate this error? So this is my present position, and let's call it 1, and this is my desired position 2. So this is my theta angle, and that's my theta d. So there is going to be theta 1d and theta 1. For the second joint, there is going to be theta 2 and theta 2d. Okay, so for every joint, it generates a servo error, and then we try and control this as a single mass system, control as a unit mass system. In the last class, we also looked at the how to reduce the spring mass damper system to the control of a unit mass by doing partitioning. Okay. So what we had done is we looked at the mass into acceleration plus p into x dot plus kx, okay, is equal to f, and what we said is this f is made up of two parts, which is equal to alpha is equal to f dash alpha plus beta, in which alpha is equal to m and beta is equal to bx dot plus kx. Now when we put it in this equation number 1, what happens is we are able to cancel out terms is equal to alpha into m into alpha plus bx dot plus kx, and what we have seen is we can cancel this and we can cancel this and this. So what we are basically trying to control is a unit mass system. This is m into f dashed. So what we are basically getting is we are able to control, or we are trying to control, a unit mass system. So this is a unit mass because the mass here is unity. Okay. So what we do here is we try and control this unit mass system by proposing a controller. What is the controller I'm going to propose now? Now the controller we are going to propose is x double dot into d plus kv into e dot plus kp into e. Okay, so this is my derivative part, and this is my proportional part. So this is PD. But you'll notice that this is in E now. And what is E? E is the servo error. So this controller now, if I bring x double dot this side, then it becomes x double dot minus x double dot here. Okay, plus kv into E dot plus kp into E is equal to 0. And this becomes my E double dot plus kv into E dot plus kp is equal to 0. Okay. Now what we are seeing is that we are basically operating in the error space now. And this is going to track a trajectory. And the moment the error becomes equal to 0, we know that we have reached. Now this kind of controllers are called trajectory tracking controllers. Now what would the control system look like? So the control system diagram would look something like this, where we have we are partitioning the control system into the model part and the servo part. So this is my robot. And this is my kp. One part is kp, the other is kv. And we have two parts which are coming in. This is my desired. So my desired xt double dot is coming there. Okay, that's my xt double dot. And we have another two taking care of the kp and the kv. So this is connected to kv, kp. And we have the bx dot plus kx here. Okay, so this is my output coming, and what we are doing is there is one which is going here, and there is another one. This is my control system now. The other fellow is coming here, and it is coming here. Okay, so now what we see is we have one input here, which is my kp, would mean that the input is xd, and here it is xd dot. Okay, and this is my xt double dot. So essentially what we are getting is this is my x dot and this is my x. Okay, so we have partitioned the control system into two parts, and this is my model part and this side is my servo part. Now what I've effectively done is that the servo part will only take care of your this is my PD controller. So my PD controller and the model part are separated now. And the advantage of this is that if there is any change in the model, it can take care of it. So nonlinear systems can be controlled this way, in which if there are changes in the model parameters, the MB and the K parameters, then they go into the model part, and the servo part, PD control, the PD part is completely separated from that. Okay, this is called my partition control system. So this is called my partition control system. Okay, now we have seen that in the previous equation, what we were getting is we had our equation in terms of E, and E is equal to theta D minus, so E is equal to, so this is theta D minus theta, and we have E dot is equal to theta D dot minus theta dot, and E double dot is equal to theta D double dot minus theta double dot. Okay, so these are the three requirements of the trajectory following controller, and we are calculating that. So theta D is coming here, theta D dot is coming in from here, and theta D is from here. Okay, so we are able to control the error, and then by servoing the error we can reach from a position to a desired position. Now this is basically called a partition control system. Now something important here is that this partition control system can take care of nonlinear systems also, and we'll see how. Now let's look a little further and see that the task of a controller is basically to reject some kind of disturbance. So the task of controller is also to reject disturbance. Now where would this disturbance come from? This disturbance is your dynamic torque TD. We have said that what the dynamics does is essentially starts disturbing the system now. And if you write our controller like this, E plus Kp into E dot plus Kp into E is equal to F disturbance now, which is equal to TD. Okay, so what the servo controller is doing is that it is taking the link from some position to the desired position, and what the dynamic torque is doing, it is trying to disturb the system now. Okay, and the task of the controller is to try and reject this disturbance. Now the moment this reaches the final position, okay, so once it has reached desired position, our so after it has reached the desired position, your E double dot is equal to E dot is equal to 0. Okay. Now, if that is the case, and we put it in this equation, so let's call this equation question number 2. So putting this in equation number 2, we are left with Kp into E is equal to F disturbance, which is equal to Td. Okay. Now, this means that this is what also we call steady state. What this basically means that at the end of the day, you have error E, which is equal to Td by Kp. This is what it means. Okay, so this means that a PD controller will always have some error steady state, okay, which is equal to Td by Kp. That means the PD controller is never going to reach the desired position. So it will go somewhere slightly before the desired position and it will stop. And this error steady state is going to be directly proportional to the dynamic torque, which is Td, and it is inversely proportional to the Kp as seen from here. So if you want to reduce error steady state, what we must do, we must move Td must be low, Td must be small. What this means is that it should operate at low speeds. So if the manipulator is operating very slowly, okay, then what happens is your dynamic disturbance also becomes small. Next is there is a gear ratio there, if you remember from the last class. Now, if you have a very high gear ratio, again, your dynamic torque becomes less. Okay, so to reduce ESS, you have to make Td small, and what you can do is make gear ratio large. This is my gear ratio, and next is it also depends on Kp. And make Kp also large. Is inversely proportional. Now this n is less than 1. So please remember that the gear ratio is less than 1. By large, I mean the reduction should be much higher, which means n is less than 1. And Kp should become large. So if you want to reduce your error steady state, then we need to do these 3 things. Increase your gear ratio, then operate at slow speeds, so the dynamic torque is less, and you have to increase your position gain. But this gives us the very interesting result that your error steady state is never going to become 0 if you are going to use a PD controller, but it will be very small, so it's still okay. Now, if you want to get rid of this PD controller, what we can do is we can add an integral term. So that is the next type of controller, which is your PID controller, in which we have E double dot plus KV into E dot plus KP into E, KP into E plus KI integral E dt is equal to F disturbance. Okay, so this is my P term, this is D term, derivative term, this is the integral term. Okay, so what we can see here is that in case of error steady state now, so error steady state, once it has reached the steady state position, Ki into E is equal to F disturbance, okay, which is equal to 0, because we are making the assumption that this is a constant disturbance. Okay, so under this condition, what we can say is that the error steady state becomes 0 by putting an integral part into the controller. Now, the disadvantage of putting this is that we are making the system higher order, it is becoming s raised to 3. Okay, and for very very high gains, it will become unstable, because the roots will go to the right side of the roots will move towards the right plane. Okay, so this is the basic theory of PD controllers and PID controllers. And although PD controllers have some error steady state, but it can be made small by looking at these 3 things. And that is the reason why PD controllers are used even in the industries. Whereas PID controllers give you a 0 error, which is good, but then it involves other problems, because the gains, high Ki gains. So if your gain Ki is very high, then there is a chance it will become unstable. And because you're integrating now, you have to, it involves some kind of a time delay now. Okay, so when we look at an actual control system, most of the control systems on robots can be PD controllers itself. Now let's look at an actual robot like a Puma 560, which is an actual industrial robot. And how does the control system exactly look like inside? Okay, so here we have a computer, which is a DC. This is a very old robot, so this is a DC computer. Okay, and from the computer we have an interface. And with this interface, basically each of the joints is controlled by one microcontroller. In this particular case, it's a very old microcontroller, 5602. It's very, very old. Okay. Nowadays, you have more recent microcontrollers, but this is for the Puma. So it has 6 degrees of freedom. So every joint is controlled by a 6502 controller. So this is my joint 1, this is joint 2, joint 3, and this is my joint 6. Okay. So the Puma 560 is a 60OF robot, and this is the basic control structure. Now in the computer, what is controlling it is a program called written in val 1 or val 2. So next we'll be looking at how to write a computer program, a robot program in terms of val language. So you write the program in the computer does all the inverse kinematics, finds out all the errors, generates the servo error, then finds out what should be the trajectory of each of the joints. From here it goes there to the interface, and in the interface each joint controller is told what should be the corresponding trajectory of the joint and in how much time, and the corresponding joint is moved by the microcontroller. Okay, so this is the basic control structure of a industrial robot. Now at the joint level, when we are looking at what is that, is we are given our theta d. This is my microcontroller 6503. Okay, and there is a digital to analog converter. This goes out to the motor, power is amplified, and this goes to the motor, and finally it moves the joint angle, and there is a sensor here. So there are encoders here, which is my feedback control system. Okay, so this is essentially what the control loop looks like at the joint level. So this is at the joint controller. The previous one was the complete robot controller, where there is a computer which computes all the inverse kinematics and all that, generates the trajectory, gives it to the interface. From the interface it goes to the corresponding joint microcontroller, and the microcontroller enforces it. So at the joint level, this is my microcontroller 6503. There is an analog to digital to analog converter, because the microcontroller is going to give a digital signal. It is converted to an analog signal. The current is amplified, and then it is given to the motor. The motor moves, the encoder takes the feedback and tells the microcontroller what is the position. Microcontroller essentially generates the error, and this is how it works. Okay, so this is how an industrial robot works at the joint level. Now in the last class we had talked about non-linearities in the system. Now non-linearities can come from different places. Okay, first of all, what we can see is that when we looked at our basic non-linear system, so when we had looked at our spring mass damper system, m x double dot plus bx dot plus kx is equal to 0. Okay, what we said is that we made the assumption that m, b, k are constants and they are linear. Now what we do know is that in the real world, this spring constant, if I draw the graph, it'll basically look something like that. Okay, and the equation would be F is equal to Q into x cubed for a real spring or a nonlinear spring. So this is a nonlinear spring. So let's call it a nonlinear spring. What about friction? We know that friction behaves something like this. So this is my friction. It behaves something like this, and this is written as B x dot. So it's a sigmoidal function. So we see that this is also nonlinear, this is also nonlinear. So now we need to see that although we have made the assumption that all these MBK are constants, they may not be constant. What about M? M is also not a constant. Why? Because the robot will pick up some mass and it's going to leave the mass again. So that M is going to vary. And with time there is going to be some wear and tear. It's very small, but it can be neglected. But a robot picks up mass. So basically it means that the mass at the end effector is going to change. So this is one. Spring and friction are two sources of nonlinearity in the system. Now when we look at the dynamic equation of the robot, we see that the dynamic equation is written in the form, this is the mass inertia matrix into acceleration plus h into theta, theta dot plus c theta plus j transpose f is equal to the joint torque tau. Okay, now we know that this is my inertia term. Okay. This is Coriolis plus centripetal. This one is gravity. This is external force. And this is my joint torque. Okay. Now we know that this is a nonlinear differential equation. So it basically means that a robot manipulator, the equation of motion, is a nonlinear differential equation. Okay. So although we talked about linearizing and all that, we can linearize the system at a point, but a robot manipulator is going to operate at different points. So trying to linearize it about one point in the workspace really doesn't help. Okay. So the other way is by trying to use the partition control system. So we are using our partition control system that we just talked about. Now in the partition control system, what we do is that we partition the nonlinear part, or all the nonlinearities go into the model part, and the servo controller, the P and the D part, remain in the servo part. Okay. So if there are nonlinearities, this is some kind of a moving moving linearization which is going on. Okay. So what we basically do is we take the spring mass damper system. Let us make the assumption that we are taking a mx double dot plus bx dot plus k into x cubed is equal to 0 now. Okay. So we have a nonlinear fellow which is coming inside here now. Okay. So kx cubed is coming in there. Now how do we take care of it? We basically partition it, and in our partition control system, so this is my xd double dot, here it is my m, then this is the summing block which goes into f is equal to mx double dot. This is my system equation now, bx dot plus, so this is k into x cubed, this is my system, and we have bx dot plus kx cubed here, and we have a kp and a kv as done before. So basically what we are doing is we are partitioning it, and so one is coming there, one is going here, and one is coming here. So there is okay. So now what we are seeing is that we have partitioned this. So what is going to happen in here, we'll get our xd, and what we are going to get here is xd dot. Okay. Now what we are getting here is we are dividing it into two parts. So this is my model part and this is my servo part. Now what you can see very clearly is that the servo part is independent of all those mbk parameters, okay, which are nonlinear. Now the model part is the one that takes care of mbk, which are nonlinear parameters here now. Okay. So in this system we are able to handle our nonlinearities, and this is one of the ways in which we can linearize the system. Okay, this is also sometimes called moving linearization, and it can take care of all nonlinear kind of systems. Now what about the robot manipulator we just looked at? So this is the robot manipulator equation, this one. Okay, how can we take care of this? So we can take care of this by putting breaking it up into two parts. One part is here and the other part is there. Okay, so what we can do is we can take the in case of mass here. So in the case of mass, what we do is we put d theta there, that's my inertia tensor, and what we do here is we say it is h into theta dot theta plus g theta plus j transpose f. Okay, so this is a way where we can partition the dynamic equation and use this partition control system to control it. Okay, now the next term that comes up is that, well, not next term, but a couple of things that come up here is that when we talked about the dynamic equation, can you compute this in real time? Okay, now the answer is no. Although you compute very, very fast, what is going to happen is it is going to still take some time. So in the case of a real robot manipulator, there are two problems that come up for using. So problems using dynamic equation are of two kinds. Okay, the first problem that turns up is computation time. Time to compute. One is d, one is h, and the other is c. Okay, it will take some. It could be very small time, but it will still take time. Okay, because these depend on theta. So when theta changes, what would happen is these terms will change now. Okay. Number two, which is more difficult, is inaccuracies in the dynamic model itself. So the inaccuracies in the dynamic model itself will cause errors. Now, what are the inaccuracies in the dynamic model? For example, we talked about D, we talked about H, we talked about C. Okay. Now, this is the inertia tensor. Now, to find the inertia tensor, you need parameters of the link. Okay. Say geometrical parameters, or what is the shape of the link, what is the size of the link. However, you'll need a lot of other things which are on the link. So, for example, nuts and bolts, bolts. Then there could be wires. Now, how do you estimate the inertia parameters of those? You cannot. Okay. So, which basically means that D, H, and C will involve some inaccuracies in your dynamic model itself. So, first of all, computation time. Second of all, inaccuracies are involved. So, which means that it is going to generate some amount of error. So, in the dynamic model that we just drew some time back, what we basically do is we use a approximate model. Okay, so it is D cap, H cap, and G cap. Okay, so basically what is done is we have to approximate these models, not exact models, but approximate models. So we basically say D cap, H cap, and C cap. These are approximate models or approximated parameters. So there are ways of approximating these parameters before you use them, because exactly computing is not possible. Okay, and there'll be a lot of errors there. So we will not go further here because we are not dealing with dynamics in this course, but this is just to understand that these problems are there. Now let's move on to the next part of our discussion, where we will talk about stability. Okay, we said that we used a PD controller and we said error steady state is there, but it's very small. Now, is the PD controller stable? Okay, we talked about a mass spring damper system and controlling this using a position regulator. So is the system stable? Okay, now we need to analyze stability, and that is we need to get into how do we actually analyze and say if a system is stable or it is not stable. Okay, so let us look at the next part, stability of nonlinear systems. So nonlinear systems, and we are going to use the Lyapunov method. Okay, so this is basically called the Lyapunov second method. So sometimes it is also called Lyapunov's direct method. Okay, so Alexander Lyapunov was a Russian scientist, and he's the first one who proposed, and hence the name Lyapunov's method. Okay, now what is the meaning of stable? There are some terms which are used, so I'll just go through them very quickly. Okay. Again, stability is a very, very big subject in control system theory, so I'm doing it very, very quickly, just basically what we need. Now, stable means for a small disturbance it will remain, for a system, for a small disturbance it will remain in a small region around the origin. Yeah, so for a small disturbance it will remain in a small region around the origin. Okay, so this is the meaning of stable. So for a small disturbance it will remain in a small region around the origin. The origin is also sometimes called the equilibrium point. Now, there is another term which is used, asymptotically stable. Okay, so these are two terms. Stable basically means for a small disturbance it will remain in a small region around the origin. Asymptotically stable means for a small disturbance it will ultimately return to the origin. Okay, so for a small disturbance it will return to the origin. Okay, so let us try to understand this. So first of all, we'll look at stable. So this is stable, let's call it A and let's call it B. So for a system which is here, okay, so we disturb it So let's say this is 2 regions. Okay, so we disturb it, what will happen? It will go somewhere and it will come here. Okay, so this is what we mean by stable. So this was my origin, and there is a small region here, let's call it delta, and this one is a small region sigma. Okay, so when I disturb it, the system trajectory will take it out of this small region delta. Okay, and then it will go round, and then it will come back to somewhere near the origin. So it will go out from here. That's a small region. It will go out like that, and then it will stay somewhere here. So basically it is saying that it is going to go out from near the origin, but it will come back to a very small region near the origin. Now this is what we mean by stable. Now we know that, so if there is a small distance less than delta, then this implies that x of t is less than sigma. Okay, where t is greater than t naught. So at t naught it was at delta, a very small region around the equilibrium position, and it was disturbed, and it has gone out, it has roamed around here and there, and it has come back to a region which is very near the origin. This is what we mean by stable. Now in case of asymptotically stable, what it basically means is that the system trajectory, if it starts from here, the system trajectory will go out and it will come back to the origin only. Okay, so this is my second part, which is asymptotically stable. So it goes off somewhere and ultimately it comes in there only. Okay, so this is the meaning of asymptotic stability. Okay, now let us look at this a little bit more in detail from the point of a spring mass damper system. Just to understand, it's much easier to understand using the spring mass damper system. So let's look at what happens in the case of a spring mass and damper system. So we have a mass, we have a spring, and we have a damper, or MBK system. Now we know that when we disturb this, if I give it a force, okay, this is my x is equal to 0 position. Okay, if I give a small force and I leave it, what will happen? It will behave depending on the values of MBK. So it's critically damped, underdamped, or overdamped. But anyway, either of them, it is going to come back to somewhere near the origin. Okay, so basically it says that if I'm going to give it a slight disturbance and I'm going to leave it, so I take it to some distance x there, and then I leave it, depending on how the values, it will come there and it will come here. Okay, so depending on the values of MBK, whether it is overdamped, underdamped, or critically damped, what will happen is it will come back to where it started off. Okay. Now, will it come back exactly to the origin? Well, you need to think a little bit about that. Okay. Now, in these 3 elements, there is a mass which has inertia, there is a spring, and sorry, I reversed this. This is B and that is K. So there is a spring which has spring constant K, and there is friction which is B. Okay. Now, what is the effect of each of these fellows? This mass has inertia. Okay. Next, B is damping. What is the meaning of damping? Damping means friction basically here. Okay. Now, what in terms of energy, what does friction do? It dissipates energy. What is the meaning of dissipating energy? So, friction is going to essentially convert your energy. What is the energy here? Energy is in terms of the force that you're giving inside, giving to the mass. So friction is going to dissipate the energy in terms of heat and plastic deformation between the 2 edges. Okay, so there is dissipation of energy. What about the spring? What is the spring going to do? Spring is going to absorb energy and is going to give it back. So there is no dissipation of energy here. Okay, no dissipation of energy. Okay, so out of these 3 parameters we see, it is only this fellow which is dissipating energy. That means it's converting the energy from whatever is given to it, it has been converted into heat, and that energy is being lost. So Alexander Lyapunov is the first person who actually observed that when you're talking about stability, whether the system will come back to the origin, it will not come back to the origin, is determined by this energy, dissipation of energy. Okay, so if energy is being lost, a system will come back. Okay, if energy is not being lost or energy is being added, then probably it will go somewhere else. So that is basically the definition of stability and why a system would come back. Now, under this definition, what is an unstable system then? So if this is a stable system, so this we say is stable, and we looked in terms of the poles, and we looked in terms of poles, etc., and we said that these poles are negative. Okay, the roots. But if this is stable, then what is unstable? Unstable basically would just be the opposite. That is, I have a region okay, and I give it some energy, what happens is it goes off somewhere else. So this is unstable now. So this is my unstable. In terms of the spring mass damper system, suppose this will not happen, but suppose you put MBK, either of them to be negative, and it becomes unstable. Then what it basically means, if I give a force, move the mass to a distance, and I leave it, then what will happen? This oscillation, instead of coming down, is going to increase. Okay, this is again an unstable system. So it is not coming back to where it started, it is going off somewhere else now. Okay, so this is an example of an unstable system now. So Alexander Lyapunov was the first person who observed that if you look at energy, then basically that is what can give you an idea about stability of a system. So let's go back and look here again. Mx double dot plus bx dot plus kx is equal to 0. Spring mass damper system. Now, what is the total energy of this system? So what is the total energy? Now we know that energy can be potential, so it can be potential energy, so kinetic energy, or potential energy. Okay. So this system, what is the different energies that it has? So if you write an energy function like this, f of x, okay, as in terms of kinetic energy, so your kinetic energy is going to become half m x dot squared, that's my kinetic energy, plus the potential energy is of the spring, okay, x squared. So in this MBK system, your energy dissipation is by B, the damping, okay, so that doesn't store energy. Now, so the only energy that is being stored is the kinetic energy, which is in terms of the mass, and there is a potential energy of the spring, which is half kx squared. Now if I take the derivative of this, then what we get is equal to mx x double dot into x dot plus kx into x dot, which if I take x dot common, this becomes mx double dot plus kx. Okay. Now from this equation number 1, let's call this equation number 3. So from 3, what we can see is that I can write it as mx double dot plus kx is equal to minus bx dot. Okay, from 3 I can write it like this, and I take this part and I put it inside there. Okay, so what I do get is v dot x is equal to minus of bx dot into x dot. Okay, so what I'm getting now is that is equal to minus b into x dot squared. Okay, now is this one negative? Is it always negative? Now what this basically says is that b is positive, x dot squared is positive, so this term is always negative. Okay, so this is saying that this term is negative. Okay, or 0, so it is either negative or 0, or it is negative except at x dot is equal to 0. Okay, so what this basically means is that if you're looking at the energy of the system, and if the energy is being dissipated, like here this is a friction which is dissipating your energy, then this your v dot x is going to become negative, okay, except at x dot is equal to 0 or x is equal to 0. Okay, so this essentially means that energy analysis proves that the system will eventually come to x is equal to 0. So this means that if you analyze the energy, analysis proves that this system will eventually come to 0, come to x is equal to 0. This is what it means, right? So we have a way of trying to analyze if a system will come back to 0 by just looking at the energy. So this essentially means that we have to generate what is called an energy function. Okay, now if you generate this energy function, take its derivative and find that it is negative, okay, semi-definite. Okay, negative definite, then it is great. If it is semi-definite, that means at x there are positions where this can become 0, then also it is stable, but we have to look at another property. Now this is one way of looking at the stability of nonlinear system. So a nonlinear system of the type x dot is equal to f of x t, or x dot is equal to, we can simply write it in terms of f of x Okay, the stability is performed. So the stability analysis is performed at equilibrium points. Okay, so the energy analysis or the stability analysis of this nonlinear system will be done at equilibrium points, which are, so the equilibrium points, that is points which are fx is equal to 0. So these are called equilibrium points. Okay, now so what is the first thing that we need to do? First of all, we need to propose an energy function. We need to propose our Vx, then take its derivative and see whether it's negative definite. Okay, so first of all, propose an energy function Vx. That's the first thing we need to do. Okay, so we propose this function Vx, and these two conditions have to be satisfied. Number one, Vx has continuous first partial derivatives. So Vx has continuous first partial derivatives. Vx is greater than 0 except at x is equal to 0. So this is the first thing that Vx must satisfy. The second thing Vx must satisfy is that v dot x is less than or equal to 0. Okay, that is Vx where v dot x is change in system trajectories. So I'll just explain this as we go along. Okay, so basically what Lyapunov direct method does, or how we use that, is essentially we need to propose an energy function. The energy function should have first continuous first partial derivatives, and v of x should be greater than 0, okay, except at x is equal to 0, and v dot x should be less than or equal to 0. V dot x is change in system trajectories, essentially. Now what the Lyapunov system theorem tells us, so the Lyapunov, what this theorem basically tells us is that a nonlinear system, okay, let me write down the theorem because these are theorems. A nonlinear system x dot is equal to f of x is said to be asymptotically stable if there exists a positive definite differentiable scalar function. So it has to be positive definite, it has to be differentiable, and there is a scalar function of the state variables Vx, okay, with v dot x being negative definite. Okay, so the Lyapunov theorem basically says a nonlinear system x dot is equal to f of x is asymptotically stable if there exists a positive definite differentiable scalar function of the state variable Vx with v dot x being negative definite. Okay, now the sufficient condition is so we have a sufficient condition of Vx greater than 0 and v dot x less than 0. Okay, this is sufficient. So in a system, if you find that v dot x is greater than 0, v of x is greater than 0 but v dot x is less than 0, then it is stable. There's no question asked. Okay, it is asymptotically stable, means it will come back to the origin. But now at x is equal to 0, what happens? Okay, so the second condition is if v of x is greater than 0 and v dot x is less than equal to 0, then we have to use the Lassalle's condition theorem, and this also proves that it is asymptotically stable. Now what is this Lascelles condition, or where does this come up to? Where does this come? So we go back to a spring mass damper system. So you look at your spring mass damper, how it is behaving. So your spring, we have a mass and we have a damper. So we have an MBK system, mx double dot plus bx dot plus kx is equal to 0 in this system. Okay. Now we said that we proved that v dot x is equal to minus of bx dot squared. But at x dot is equal to 0, okay, this v dot x is going to become 0. Okay, so v dot x becomes equal to 0. So it is not less than, it is not negative anymore. Okay, it is not negative definite, it becomes negative semi-definite. Okay. Now, where would this happen? So we have an equilibrium point where x is equal to 0 is an equilibrium point. So what is going to happen if this is moving in one dimension only in x. So if this is my x-axis, so x is equal to 0. So if I push the mass and I leave it, what will happen? It will start oscillating. That you can imagine. Now what does this oscillation means in terms of x dot? So first it will go this side, then it will come back this side, then it will go that side, then it will come this side, then it will come this side, then this is what it will start doing. Okay, so this is oscillating about this point. So it basically means that all these points at the extreme ends, the velocity x dot is going to become 0. Okay, so at those points v dot x is 0 now. Okay, so what in this particular case, what we see is how many points are there? There are infinite points. If this is my 0, so this is 1, 2, 3, 4. In this direction it is infinity, in this direction it is again infinity. Okay, so there are infinite number of points actually where your x dot is going to become equal to 0 for the spring mass damper system. Now what the Lascelles theorem tells us, okay, before we go, there's another point, another case where this happens is if you look at an inverted pendulum. This is my inverted pendulum. It is swinging from one end to the other end, here and here. Okay, so it is going from here and it is going back there. Now at these two locations, at here and here, again your theta dot will become 0. Okay, now is there any other condition? Now if you think a little bit, you'll see that there is another condition which comes up. What is that? Suppose it is rotating and goes on the other side now. It has gone like this and gone that side now. Okay, there also x dot is equal to 0. Oh sorry, theta dot is equal to 0 there. The velocity is 0 there. Okay, so your theta dot is equal to 0 even in this location at theta equal to 90. So if it's from here, it's 1. Sorry, from if this is my 0, if I say this is my 0 degrees, then that is 90 degrees. So we are seeing that the system can become 0. The velocity can become 0 at more than one location now. Now what happens to such systems? Because they are not negative definite, they are negative semi-definite. Now if you look at this spring mass damper system, we have the mass which has moved here or it has moved here. Now in this end point, what happens is can the mass go there and sit there? Can it wait there? No, it cannot. It has to immediately go back. Now why is that so? Because once you give it a small push and the mass has gone here, what would happen is the spring is compressed now. The moment the velocity becomes 0, the spring will push it back. Okay, so what is happening is at that extreme points, the mass is subjected to an acceleration in the reverse direction. Okay, so at the end points, here, there is an acceleration which is pulling the mass backwards now. And this position, there will be an acceleration in that direction. Because of which, although x dot becomes 0, at x dot is equal to 0, the mass subjected to an acceleration which is going to pull mass subjected to acceleration, okay, which is going to pull it back again. So what is happening is that it is not a kind of a stable point. Okay, the mass cannot go and sit there. It will immediately go in the reverse direction. And the only stable point is here at the equilibrium point. But that is, we can intuitively understand that this is why it is happening. That at the extreme points, the mass is changing. The mass is subjected to an acceleration and it is coming back. But how can we prove that? So we have a second theorem which is called the Lascelles theorem. Okay, for semi-negative, this is semi-negative definite systems. Okay, now what this says that let